Welcome and hello. This is a video exercise using the FHWA hydraulic toolbox. And in this exercise, we're going to be doing some storm drain sizing. So what I have on the screen here is the problem statement with given data. At the very top, we're asked to find the minimum storm drain diameters. That is D12 and D23, the diameter of the storm drain from point 1 to 2, and then point 2 to 3. We're given some pipe data as well as some storm/watershed data, which we will be utilizing during the calculations. All right, so for the pipe data, real quick, we're setting a maximum depth as half of the diameter. So lowercase d is what I'm using to designate the depth of water in the storm drain. Capital D is what I'm using to designate the diameter of the storm drain pipe. Both pipes are 100 meters long, and then the slopes are different. So slope 1 to 2 is 2.3%, and then slope pipe 2 to 3 is 1.5%. 0.015 is 1.5%. For the storm data, we're using the 10-year storm event for our design. We have a latitude, longitude, as well as some basin properties. So let's go ahead and get started. My plan of attack here is to work from upstream to downstream, which means we're going to look at basin 1 first, and then size this pipe from 1 to 2, that diameter, and then look at the basin 2 data at peak flow rate, and then add the flow rate to basin 1, figure out what the time of concentration is, and then lastly, determine the diameter for this pipe from 2 to 3, which is D23. Okay, so I'm going to minimize that and come over here to the hydraulic toolbox. Move my toolbars and buttons up there. Okay, here is my project. I'm going to right click and start by adding a rational method analysis and then double clicking to specify the parameters. Again, we're going to be starting with the upstream basin, which is basin 1. So over in my notes, I was given A1 and C1. C1, the runoff coefficient is right here, 0.62. And then the area is in hectares, that is 10 hectares. If you're not already using metric, go ahead and switch that over. So you can do that by this drop down right here, or units and metric. So back to the action. The rainfall intensity, we don't have that yet, but we do have some other clues such as the latitude, longitude, the design storm, and the time of concentration for both basins 1 and 2. So I'm going to click on the compute button. And then what I'm going to do is click on this get NOAA Atlas 14 data, type in the latitude and longitude. So 40.94 is what we're given for lat. Negative 78.97 is west longitude. So I will click on OK and then wait for a moment. And then notice that we have all 0 data. So this is a little unfortunate, but it's just a little bit of a hiccup in the program because we're using a metric is what I think is happening. So what I'm going to do real quick is close that, click OK, change the unit system to US customary, which is the exact opposite of what I just told you to do before. Reopen up this calculator, click on compute, and then basically type in the same lat long that we did before, 40.94 negative 78.97, and then click on OK. Wait for a moment. And there is our data. Now, these numbers are in US customary units. So we're looking at intensities here in inches per hour. So if I clicked on a return period, we're using 10 years, so we'll click on that. And then I specified a time of concentration, say 25 minutes, and clicked compute. It's giving me this intensity in inches per hour. We don't want that. We want to be using millimeters per hour. But what we can do is take this data in inches per hour, convert it to millimeters per hour, and then manually input that data in this form right here. Okay, so it looks like it's already added, but again, this is in units of inches per hour. So I'm going to click OK, bring up an Excel file that I have prepared for this very purpose. All right, so we're looking at 10-year intensities for the 10-year storm, which is the row in the table that I have already selected. And I know the numbers are kind of small, but over here in this column 3, this is reserved for inches per hour. Type in 6.25, 4.82, 3.96, 2.70, and 1.75. I think that's it. This text is so small I can barely see the difference between a 2 and a 3. I think that's it. Okay, and then to convert, we just multiply inches by 25.4, and then copy that for all of the durations, just the formula. So here are the values that we're going to use for millimeters per hour for our 10-year return period for the durations of 5 minutes up to 60 minutes. All right, so I'm going to just move that over to the side, click Done, click OK. Come back here and change it to metric units again. Open up our same calculator, click on Compute, and it looks like we still have the same numbers here for inches per hour, even though we've switched the units for our hydraulic toolbox. So I think that's fine. What I'm going to do is click on Define Storm Data, and then for the 10-year, which is already selected, okay, so it looks like the numbers are already converted. Okay, so maybe I didn't have to do all those steps, but anyway, these are the numbers I would have typed in if they weren't already converted. So cool. I think we're good. I'm going to click OK and just do a quick test. So again, just making up 25 minutes for the time of concentration, clicking on compute, and the intensity is now 76 millimeters per hour, which makes sense. In fact, let's go ahead and try 15, compute, just making sure that the units and the numbers are in the correct ballpark because these numbers right here continue to report in inches per hour. Plot looks correct because look, the intensity is up in the hundreds and 200s. So that's good. So I'm now going to actually use the time of concentration that we've been provided. So for basin 1, which is what we're dealing with, the time of concentration is 28 minutes. So click on compute. Okay, 71.898 is our intensity in millimeters per hour for basin 1. That is the last thing we need to actually compute the flow rate, the peak flow rate from basin 1 for this 10-year storm. So I'll click on Done. And okay, so it rounded to 71.90. That's all right. Time of concentration is our 28 minutes. And then the flow rate has calculated right here to 1.2 cubic meters per second. Now, I mean, the fact that it's rounding is a little bit of a problem for me because ultimately this could be anything from 1.15 to 1.24999. I went ahead and did this calculation. The actual number is 1.238 cubic meters per second. It just happened to be rounded to 1.2. So I'm going to be using the more precise flow rate in just a moment when we get to the channel calculator. But we're ready for that now. So let's go ahead and click OK. And then for my project, I'm going to add a new channel analysis. By the way, I want to keep track of my different elements. So I'm going to rename this rational method analysis and just call it basin 1. And then for the channel analysis, I'll rename that. And I'm going to call this storm drain pipe 1 arrow 2. So the inflow from basin 1 will be entering storm drain pipe 1 to 2. So let's go ahead and do that. The shape is going to be circular. The pipe diameter is what we're trying to figure out. So I'll skip that for now and come back to it. The longitudinal slope, I was provided that in the problem statement, that is 2.3%, so 0.023. Manning's roughness is also given, 0.011, so that's typical for pipe. And then the flow rate, we are given the flow rate as well, or that's what we just calculated, 1.238 cubic meters per second. Okay. So we need to provide a diameter, and we want that diameter to result in a depth calculation, which is half of the diameter. Another way of doing this is to set a pipe diameter and a depth to a point where the flow rate that's calculated equals the flow rate that we want it to be based on our previous calculations. So I'm going to operate using the former strategy where I just set the flow rate and the diameter, and we check to see if the depth is equal to half of the diameter, and then adjust with each iteration until it is exactly correct. In the second pipe for storm drain pipe 2 to 3, I can demonstrate the other strategy if anyone's interested. All right, so let's just make some absurdly large size pipe and work our diameter down until we hit our target. So I'm pretty sure 6-meter diameter is too large. Just for grins, let's click on calculate. The depth calculates out to 0.218 meters. So if this happened to be half of the diameter, we'd be right on. But of course, it's far less than half, far less than 3 meters. So let's just decrease that pipe diameter to 3 meters, or how about 2 meters? Calculate. Okay, the depth is a little higher, 0.29. Let's make the diameter 1 meter. Calculate. Okay, getting closer. This is 0.367. How about 0.8 meters? I'll click on compute, and the depth is also down here. So 0.41 meters, 0.41 meters. It is actually a little bit too small at this point because 0.41 times 2 is a little bit larger than zero point 0.8. So let's try 0.8 and then calculate. Okay, that's a touch too big. Let's go with 0.81. Calculate. So 0.405 is slightly more than half of 0.81. So it looks like to the nearest centimeter, 0.82 meters is the smallest that our diameter of that pipe from zero point 0.1 to 2 can be sized. And that results in a pipe depth of 0.405 meters. Okay. So that is our answer for the first half, the first type of the two pipes. Diameter D12 is going to be 0.82 meters or larger because in reality, manufacturers probably don't have custom pipe sizes like this. You'd probably just round up to the next size, which is, I don't know, 1 meter, maybe a 0.9 meter available. I'm not sure. So I'm going to close up this calculator. We've done basin one. We look at our map here. We've calculated the flow rate and all the data for basin one and the pipe 1, 2. Next, let's check out basin two and then ultimately work on the pipe from 0.2 to 0.3. Okay, so back to our calculator. I'm going to take the properties from basin one and just right click and duplicate. Hopefully we won't have to jump through all the same hoops we did the first time with regard to unit conversion and the intensities. So I'm just going to rename this to basin 2. At the moment, it's an exact copy, but we're going to be changing a few things here. So edit the rational method data. Right, so the runoff coefficient we were given is not 0.62, that is for area 1. It's going to be 0.44. The area is not 10 hectares, but now 16. And then the rainfall intensity, we don't know that, but it's a time of concentration of 42 minutes. So if I click on compute, and then it looks like this is where I left off, hopefully changing the time of concentration is all I need to do. So from 28 up to 42, click on compute, and we're given 56.188 as the intensity. That looks correct. I expected it to be a little bit less than 71, but not single digits small like we see in this table. So let's go with that 56.188. If I click on done, that number gets copied here. It's all rounded 56.19. And then we're also provided a flow rate from basin 2 of 1.1 cubic meters per second. When running this calculation myself to the nearest thousandth of a cubic meters per second, it actually came out to 1.099. So effectively the same thing, but I'm still going to use 1.099. All right, so that was basin 2. That was much quicker. Now we have our flow rate from basin 2 that's contributing to that pipe 2, 3. So back to the map, pipe 2, 3. However, the time of concentration in basin 2 is 42 minutes, and from basin 1, it's 28 minutes. However, the contribution from basin 1 also has the travel time through this pipe, which is 100 meters long. Now, I don't think it's going to take 14 minutes to travel from point 1 to 2 if it's only 100 meters. Let's go ahead and check the velocity through the pipe. So here are our results. Average velocity is 4.7 meters per second. So it's going to take, I don't know, maybe 20 or 25 seconds to travel from point 1 to point 2. Okay, so that's pretty much negligible. The length of this pipe is way too short for the basin 1 time of concentration to control the combined time of concentration at point 2. So what I'm going to do is recompute basin 1 solely for the purpose to determine its flow rate, its peak flow rate contribution at point 2 using the larger time of concentration of 42 minutes, which is that for basin 2. Okay. Anyway, what I mean by that is I'm going to make a copy of either of the basins is fine. In fact, it'd probably be a little bit easier to make a copy of basin 1, duplicate, and then I'm going to rename this. And then in parentheses, I'm just going to say at 2. I'll know what that means. And then I'll double click. And what I'm going to do here is using the same runoff coefficient and area as the original basin 1. That doesn't change. But the time of concentration is going to be 42 minutes. And if I tab off, okay, good to see the intensity decreased as I expected it to. And then we have a flow rate of 1.0 cms. So this is will be an adjusted flow rate, peak flow rate from basin 1 from the perspective of point 2, not point 1 anymore. And when I actually ran the numbers, this wasn't 1.0. If we want better precision, it came out to 0.968 cms. Okay, so what I want to do here is add up the two different flow rates. At point 2, the basin 1 contribution is going to be 0.968, and then add that to my 1.099. That's going to give me a combined flow 0.2 of 2.067. So here is the final calculator we're going to add. I'm going to start by duplicating the storm drain pipe from 1 to 2, rename that, and then call it 2 to 3. And then I'm going to have to modify a few values here, such as the slope. I'm given 1.5%, 0.015. The Manning's roughness is the same. Now we know that this flow rate right here needs to be 2.067. But what I'm going to do is use that second strategy of defining the pipe diameter and the depth, and then trying to get a flow rate that equals 2.067. So as before, let's just go ahead and start with a larger diameter than we really expect, and then click on calculate. So if the diameter is 2, the flow rate results in 11.018 cms. That's way larger than 2.067. So let's decrease the diameter to, how about 1? So half of that is 0.5. Clicking calculate. 1.735. That's too small, actually. So let's go with 1.2. Half of that is 0.6. And calculate. 2.82. Okay. So we know it's between diameter of 1.0 meters and 1.2 meters. Let's try 1.1. So 0.55. Calculate. 2.237. So that's a lot closer than anything we've had so far. Again, we're looking for 2.067. So let's drop it down a little bit. How about 0.8? That is 0.54. So calculate. 2.131. Okay, it needs to be less than that. About 1.06, and 0.53 meters would be the depth. And calculate. 2.027. Okay, again, we're looking for 2.067. So let's increase it 1 more centimeter here. 1.07 meters, and then 0.535 is half of that. Calculate. 2.078. Yeah, that's the closest we're going to get, at least to the nearest centimeter precision on the diameter of the pipe from points 2 to 3. Okay, that's cool. So let's close that up. And then just as a quick summary, what we did was determine that the diameter in pipe 1 to 2 would have to be at least 0.82 meters. And then the pipe from point 2 to 3 would have to be at least 1.07 meters. This is the end of the exercise. That is the answer that I came up with using the hydraulic toolbox, specifically the channel calculator, as well as the rational method calculator.